Welcome to the UIUC Talkshow. Our goal with this show is to introduce you to the most interesting people with the most interesting ideas. Today we have a very special guest. The way how we describe Dr. Allen, he is probably one of the few really unique minds of the last couple years in this campus. He has a very interesting story of working at one of the, what I would say and describe as one of the weirdest and most unique places in the world in the 1900s. That place was called Bell Labs. And if you don't know what that was basically a place where the brightest people from the United States and the world came together and discovered one of the most impressive and useful things that we use today. Welcome, Dr. Allen.
Well, thank you.
I'm super excited to talk to you and really talk about your ideas and really get to know you a little more. So you spent about, if I remember correctly, 32 years working at Bell Labs. And what you say was your lifelong pursuit, your lifelong goal. And that goal was human speech recognition or processing. What is something that usually when you tell people are most surprised about, or what was the most surprising thing you discovered?
Well, let's move up on this a little bit more slowly.
Okay.
When I went to Bell Labs, I just wanted to find a problem that was interesting to solve that was hard enough that it was going to take a while to do it. And when I was there for the first year, I worked on some mundane things, but they were interesting, like an ultrasonic telephone. They wanted to make wireless telephones. There were no wireless telephones back then. So we wanted to make wireless telephones, and we did. Anyway, so I worked on some of those things, and then I was introduced to the research department, and there I learned about studying the ear, the inner ear. And that struck me. That's a problem that's hard enough to work on. I'm going to be working on that one for a while, and it's a worthy problem to solve. And Bell Labs, what's their business? Their business is speech, transmitting speech back and forth, Hello, Mabel, I'm here. So it was considered to be a very valid thing to study. So then I went from there to working on studying the brain of a cat, sticking electrodes in the brain of the cat and putting sounds in. We had loudspeakers specially made, put them in the ear, and then we'd play the sounds in different tones and then try to track down where the sound went in the auditory nerve and what it looked like. And it just got worse and worse, or better and better, depending on your opinion. And I started modeling the cochlea and really got heavy into the math. And Bell Labs was very happy with what I was doing. They were proud of it. And as long as you're successful in doing something that is considered to be relevant and important, then they're happy about it. They let you do it. Now, you're asking me, what did I do? It's a pretty big question. So we were just talking a few minutes ago. One of the first things I worked on is speakerphone. So speakerphone is a phone that sits on your desk. It's a hands-free phone. And tell me to stop talking if I'm talking too much. So it's a hands-free phone, and it didn't work very well. So you get feedback. There was problems with the room reverberation, all sorts of issues. It basically didn't work very well. So we worked on that problem, designing a loudspeaker that was not feeding back into the microphone, and there's switching circuits inside so that when you started to talk, the loudspeaker would turn off And when you stopped talking, the loudspeaker would come on so you could have a natural conversation. And worked on that for a while. And because of that, I got interested in room acoustics, because room acoustics was one of the really serious problems. Room acoustics, this room is dead, but if you're in a classroom or you've heard people talk on the phone when somebody calls them up and they're being interviewed and you can barely understand what they're saying because it's just all this reverberation. So he said, got to deal with that. So I worked on a model of reverberation. I was telling you a few minutes ago that I worked on this model about treating a room and the walls are like mirrors. So if you have a source in front of the wall, there's another source on the other side of the wall, which is basically just a reflection. There's not really a source there, but if you go look in a mirror, you can see many, many copies of yourself. You have two mirrors on either side, and you look in this mirror, then you see the reflection of that mirror, and that mirror has a reflection of this one, and you can just see an infinite number of mirrors. Well, it's the same thing with room reverberation. So I said, well, that's not so hard. So I treated the room as all of these reflections that are infinite number of reflections. And it was a kind of a trivial little exercise, but a paper is just cited huge number of citations, a couple a week to more than that. And so that was fun. It's the kind of thing I was looking for. It was interesting. And then I went from that to, I learned signal processing, which is pretty much a well understood topic today. Ask me another question.
So I do want to keep going on Bell Labs, but I do want to ask you, when did you know you wanted to do all of this? So
when I was 8 years old.
Keep going.
I don't know how it happened, but my grandmother gave me an old radio that she didn't want, and I took it apart. I took all the pieces out, and I thought, okay, now I got to put them back in. Well, I couldn't even begin to do that. Didn't have a clue how to put them back together again. So it fascinated me, and back then I learned how to use vacuum tubes, which were what all the radios were made from, vacuum tubes. But I don't know how old I was, but the first transistor was available commercially, and you could buy one for $1. And it was about this big and had 3 wires coming out of it, and there was a book you could get for another $1, and it had circuits in there, and you could build those things. So I built at least half of the circuits that were in that book, burned up a lot of transistors, but they were $1 each, and no big deal. So the transistor, of course, replaced the vacuum tube, and we wouldn't have computers today if it weren't for those silly little transistors, which were not invented here, but the guy who invented them was at Bell Labs, and he didn't like his boss very much for pretty good reasons. The boss was pretty nasty to him. His name was John Bardeen, and he left Bell Labs and he came to the University of Illinois. And he had invented the transistor. And Bardeen tried to take credit for it, but not Bardeen. Shockley tried to take credit for it, but Bardeen just ignored him and did his business. Then he got another Nobel Prize, that. Right. In superconductivity, I think. So he really had very, very deep insights. And so that kind of human being is inspiring, and you think, well, how did he know all of that? How did he do that, Well, you can read about it. He had a very good mentor, and he understood the concept of what was going on. And apparently, very few people did. But he started with the simplest thing, take a piece of quartz and you put something on there and it's piezoelectric. You know what piezoelectric is? You put a voltage on it and it moves, or you move it and it creates a voltage. And he said, something's going on there. And then he traced that down. And then there's also a crystal radio, a diode. You put a piece of wire on a certain kind of metal or conducting semiconductors, and it converts radio waves into audio waves. And he was fascinated with this. I don't know that much about Bardeen. I wish I did. But he figured it out, and there's no question about that. And Shockley, meanwhile, was gone. He was out in Stanford. And while he was in Stanford, Bardeen and his colleagues were inventing the first transistor, which then Shockley came back and he was really upset about it. He tried to take credit for it, but that was pretty hard to do at that point. So I'm not sure what I'm even talking about. But at 8 years old, I was thinking about this and I was fascinated by it. And that's the way the human mind works. It just gets caught up in some crazy thing, and it's designed. The human mind, of course, wasn't designed by a person. I don't want to get into the philosophy of where it came from, but the human mind is very, very good at teasing things apart, and that's what makes the world go round.
So your grandmother gave you this radio,
Mm-hmm.
but you still needed to have the.
All I needed was a pair of wire cutters.
Right, but something inside of your head told you, okay, I want to figure it out, because I'm sure your grandma and many other times probably have, gave you some other thing, but you decided not to go further.
I forgot this until now, but she also had a television set. It was about this big. It was a small portable television set, and it didn't work. And this was later. It was after that. It was a few years later. And I could tell you how I did it, but it's not that interesting. But I figured out what was wrong with it, and I fixed it. And I gave it back to her, and she was just like... So it was a broken wire on the circuit board. I traced it down. It was actually took me a long time to figure it out, but I was motivated. And so I figured it out, and then I saw, oh, that's what the problem is. And so I fixed it, and I presented the television set back to her at that point. She was just like, couldn't believe it. So there's a big reward there, right?
That I'm sure gave you like a positive feedback loop for you to keep going.
Hey, I'm not very good in the English class and I can't spell very well, but I can do this kind of stuff. Now I understand my spelling problem because it's very easy to look a word up on your electronic dictionary on your computer. So when I write a message and then I go and do the spell checking, I make sure that I know exactly why I didn't spell that word. So I know what my deficiency is. And it's very simple. Is an E or an A or an I? So I get the vowels wrong. Or I leave the whole syllable out, but that's easy to figure out because you just sound it out, dun, 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 and you say, oh, I left out a syllable there. So I can put it back in, but I don't know what vowel goes with it. So about 50% of the time I get the vowel wrong. But I look at it, I think, it's not right. And then I try another vowel. No, that's not right. Try another vowel. Yeah, that works. But now you just hit the spell checker and it tells you what it is. So.
Yeah, and I don't think it's necessarily your deficiency. I think it has to do more with the English language, because every every like every
There's
vowel.
not a unique mapping with the vowels. So
Right.
there's 20 vowels. You may think there are many fewer of them, that there's 20 vowels and 20 consonants. And you can calculate the entropy of them. So that's log base 2 of the number. So it's about 4, 4.1, 4.2. So 2 to the fourth is 16, right? So 2 to the 4.3 is like 20, something like that. So it's about 20 vowels and 20 consonants. But the number of vowels in the English language is only like A, E, I, O, U, A, E, I, O, U. So 5. So we're missing 15 of them. So what they do is they let A be several different letters and E be several different letters, and it's pretty stupid. There's the long vowels and the short vowels.
Yeah. Yeah, I do remember when I was learning English, because sometimes you had words like apple, and then but that word when you say a, you don't say you say a. So I was really confused. So and then I was trying to figure
Well,
it
you
out.
don't say apple.
Exactly.
You say apple. You don't say ipple.
Right.
But those would all be perfectly valid ways of pronouncing it.
So I was really so I was really confused. Is there something wrong with me, or what's going on here? Because I think I remember one time actually, I was like reading the stuff, and I think I remember saying something about like apple. People looked at me weird, like apple? You mean apple? Like, oh wow.
Well, you still make subtle mistakes. I can hear them.
I'm sure all the
You
time.
probably don't even know it, and it's not a very good idea to go around correcting people. But how long have you known English? 4 years?
5 years, yes.
Wow, you're amazing. I wouldn't worry about it.
Yeah.
But the brain, so this is something that I learned from studying reading disabled kids, that you learn automatically, and my granddaughter is a good example of this. By 2 years old, she's fluent in talking. She has a huge vocabulary. 2 years old, and what was that word that I told you? She says it's goofy. She's walking around saying everything is goofy. She's 2 years old. So you learn to talk, and you hear and you talk, and this all comes naturally. Reading is a completely different story. You do not learn how to read on your own. It's extremely rare for somebody to learn to read. You have to be taught to read. And if you don't have, we just submitted a paper on this, and I hope it gets accepted, but these kids who can't learn to read, and it's like 20% of the population, young kids, like 8 years old, they can't learn how to read. And the teacher works with them and they can't learn how to read. The problem we showed, and it's a fact, that they don't know their consonants. So they can't identify the various consonants. Whereas normal reading kids are very good at it. They make very few errors. Now they hear the sound and they know. I mean, I have a problem with the vowels. Lots of people do, for the reasons that you just said. There's not a unique mapping. There's long and the shorts, but you got I'm getting into too much detail here. There's something called encoding and decoding. So you look at the letters and you have to say the sound. You hear the sound, you have to write the letters. This is a complicated mapping. It's incredible. And yet a lot of people just pick it up. You show them, Johnny went up the hill, Jill and, they figure this out. What's going on up here is they're wired to allow it to be taught, but they don't learn it naturally.
I met your granddaughter, Mina, the other day, and to say she's good is a massive understatement. So tell us more about what you did with her specifically, and also what you learned about learning disabilities and the relationship with hearing.
You want me to tell you my life story?
and yes, and please go.
No, so
details
Mina went to the doctor this morning or yesterday. I don't remember which. I think it was this morning. And Mina started talking. And the doctor was flabbergasted. And she told my daughter, she says, I wasn't there, so I don't want to, but Elizabeth said that the doctor was blown away by her speech, which is consistent with what you're saying. And we know it's true. So how did this happen? Well, so I'm very, very interested in speech perception. I spent a lot of my life studying it because I was working for the telephone company. I was working how the ear works and how the brain processes the signals coming from the cochlea, blah, blah, blah. And I want to find another nice problem to work on. Well, speech perception is probably a pretty good problem. So I studied that. And when I came to the University of Illinois, I wrote a lot of papers on that with my students. So I appreciated the subtleties of this whole process. It's one of the most important things that the brain has to do is to decode sound. So it's kind of an off topic. I think I mentioned this to you. If you had the choice of losing, or you don't have the choice, you're forced, you have it, they put you in a room, they say, we're going to either cut your eyes off or going to cut your ears out. Which one do you want do you want to keep? Everybody says my eyes. That's actually the wrong answer, because when you hear, you also speak, and it's a two-way channel, communication channel. You're speaking, you're hearing, you're speaking, you're hearing. It's a communication thing. But with your eyes, you can't speak with your eyes. You can read, you can input, goes up here, you can think about it, but sound doesn't come out of your ears because you see something. Light doesn't come out of your eyes. Sound comes into your ears and sound comes out of your mouth. It's, from a human point of view, it's much more important to have the oral system in operation, where, nobody wants to lose their eyesight, but from a psychological point of view, speech is more important. And so I was fascinated by this topic and really spent a lot of time studying it, figured out what is it about the speech sound that makes a ta different from a da. So I know the answer to that question because we did some experiments and figured it out. And my student worked on that, Fei-Pong Lee. He's now at Apple. What's he doing there? I don't know. He can't tell me.
Probably in Siri, maybe.
Can't say. Don't know.
Yeah.
So anyway, that's kind of like a little piece of it. So Mina, when she was 1 year old, probably 9 months old, I don't remember how old she was, but she was not much bigger than this. And I would, on purpose, I would move my lips like that. And I would go ba, 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 ba. And pretty soon she was doing it too. And we just kept working on it. The whole family was into this thing, trying to get her to talk. Boy, did she learn how to talk. And because of this reading problem about kids who can't learn how to read, I said, I want to make sure this kid knows all those sounds really, really well. And the first way you learn that is you speak them. You hear them and you speak them. You hear them and you speak them. And so I really worked on her, and so did my daughter, and so did my wife. We all were working on her to do that. And it paid off. If you consider talking at the age of 2 paying off. She can't shut up.
But she also knows, I believe she doesn't know the numbers, but she also knows the prime numbers.
That's kind of a cute story. So when she first started to count, she got 1, 2, 3. She was watching Sesame Street or one of those programs, and she got up to 3. And when she got above 3, then she just went on the primes. And I went, what? She went 1, 3, 5, 7, 9. No, 9's not prime. So 11. She did that. And then she's got 1, 2, 3, 4, 5, 6, 7, 11. And now she's up in the 20s and she's doing 17, 19. It's consistent. I should have gotten this recorded. I can't believe it, that she intuitively this may just be a bunch of hokey stuff. I can't believe that it's true. But I've listened I understand the situation with the primes. The primes are the basic number set. All other numbers are composed of primes. Like 3 squared is 9. 9 squared, 81. Every single number has a unique representation in terms of primes. This has been understood way back from the beginning, from the beginning of science. And the Greeks, they understood that. Something called Aristotle's sieve. How can you find the primes? This is it's actually interesting concept.
Tell me.
How do you find the primes? Well, you write down all the numbers in my book. I just copied it from somebody else. You write down all the numbers from 1 to 50. This is as a starter. So 1's not a prime, so you take that out. And 2 is a prime. So now you make all of the multiples of 2. So 2, 4, 8, 16, 32, 60. Cross them all off. Okay, now what's left? Well, there's 3. So 3 is a prime. So you might make all the multiples of 3. So you say 3, 6, 3 times 3 is 9, 4 times 3 is 12. You can cross all those off. Well, you can see this is going to get rid of all the numbers pretty fast, because most numbers are multiples of various primes or multiples of themselves. So the next one is 4. Well, that's already been crossed off. Next one is 5. Oh, that's a prime. Next one is 6. Well, that's crossed off because it's 2 times 3. Next one is 7. Another prime. Now 8, that's 2 cubed. 9 is 3 squared. 10, 2 times 5. 11, another prime. So there's a really magic discovery that between every prime and 2 times that prime, there's always another prime between them.
Say it again. So
pick a prime.
13.
Keep it. So what's twice that? 26.
Yeah.
There's guaranteed to be at least one prime between every prime and its double.
17 is 1.
Yeah. So if you get 2, okay, 2 is a prime. 2 times double that, it's 4. Well, 3's in between it.
Oh, very cool.
And you can refine this instead of saying between every prime and... So there's a little saying by Chebyshev. He's a mathematician, and he has a limerick about it, which is in my book. I don't remember it, but there's always a prime between a number and twice that number. And nobody knows why, but it's not very surprising if you think about it for a while.
Who knows? Maybe you will find something.
I'm not even thinking about it
there. But you do think about math problems.
Yes, definitely. But back to Mina. Why in the world, when she doesn't know the next number, she goes to the next prime? This is just amazing. I really don't believe it. But that's what she does. And she started off down there in the low numbers. She couldn't figure out, she didn't remember 4, so she jumped to 5. And then she jumped to 7. But now the numbers that she's missing, I think she was counting today, she would hit 13, and she skipped 14, and skipped 15, 16, then she went to 18 or 17. She went to 17. She skipped a bunch of numbers. I can't believe it.
And it turns out to be a prime number.
She always jumps to a prime number. Now, it's just not observant enough. Maybe it's not true. But I can't believe it. But I've observed it many times.
A little, beauty of perhaps a gift of life, having your granddaughter to teach you.
Yes, definitely. You don't have to convince me of that.
Something that I find interesting, going back to Bell Labs, like Richard Feynman always would say, if you don't work on important problems, it's unlikely you would do important work. Or Mr. Hammond, he would go around.
Hamming was at Bell Labs.
Right. And Hammond,
Feynman was not.
right. Um, Mr. Hammond would go around on the lunch tables, and he would ask people, what's the what are the important problems in your field, and why you're not working on them. And he says, he has some stories about how he went to the chemistry table, and he asked a question.
He'd sit at the chemistry table
and he got kicked
every
out.
day. And then he sat at the physics table. So that's where he learned a lot from it.
But something about Bell Labs that allow people like you to work on important problems. And perhaps that's not a behavior that is not rewarded in today's academia.
I don't know.
What do you think?
Well, I don't believe that. But it would be easy to make the case because most people don't work on hard problems. But that doesn't mean that it's not happening. I mean, what do we know about 300 years ago? Do you think there were more people working on difficult problems 300 years ago? I doubt it. I think there's more people working on difficult problems today. But they're so few and far between that you can't get good statistics on it. We just know about the famous people who did very, very good math. But we're ignoring all the people who didn't do anything but figure out where they're going to get their lunch tomorrow. So I don't think there's any statistical evidence that that's true.
Well, perhaps that was a framing issue. When I say important problems, I say important problems that
what is an important problem?
Feynman would say an important problem is something that you can contribute to, or that you can push the ball forward.
That's almost not a definition. Important problem. Is it an important problem to pick lint off your socks, which I was doing a second ago? No. Is it an important problem to figure out how to remove salt from ocean water? Probably. Is it an important problem to go to the moon? I don't know. Maybe it's a terrible idea because you can't get back. I don't know. I mean, what's an important problem? It's a very ethereal question. I mean, what is an important problem? Well, I'm working on an important problem that I discovered not too long ago. How do you find the roots of a polynomial? Well, Newton solved that problem. And it's really interesting, his solution. But if you look in Wikipedia, it's called Newton's method. If you look on Wikipedia, or you look in the textbooks, or you look anywhere, they tell you, well, Newton's method is a pretty cool method, and some of the time it works, but it doesn't always work. I believe it always works when you apply it properly. And I'm not going to talk about that part. I got in a fight with somebody. It was, when I say a fight, we weren't hitting each other, but there was disagreement and emotional disagreement. Well, when you get emotional disagreement about an intellectual problem, you've got an interesting problem. There's the definition of an interesting problem. Two people who are of normal intelligence or higher can't agree on the solution. And they're willing to yell at each other about it. That's an important problem. That's a problem that's worth solving. There's an expression at Bell Labs: don't solve problems that aren't worth solving. That probably gets as close to it as any.
But you still pursue. So deciding on what problems to work on it takes a lot of effort and commitment and drive.
There are no rules. I mean, we were talking yesterday, I think it was, about Feynman, and I was telling you about something I read about him, that he saw somebody throwing a frisbee, and the frisbee didn't just go smoothly through the air, it wobbled like this. And he thought, that's weird that that's doing that like that. So it's something about angular momentum or something like that. And he said, it's probably in that book, The Pleasure of Learning, something like that.
Learning things, something.
And I'm not sure if that's, but I saw that book on the table in my house. I didn't put it there, so I probably must have picked it up and read this out of, I don't know where I got it, but he then said that he studied that problem just because he found it interesting. He had an intuition that it was interesting. It was a hard problem to solve. A couple of years later, he got the Nobel Prize because he applied that solution to electrons and figured out about the spin, and the spin of the electron is a wobble just like that frisbee going through the air. And he got the Nobel Prize for it. And there were some Hans Bethe, famous physicist, they were all at Cornell, and Bethe, who far more famous than Feynman. Feynman was a student. Bethe kept saying, "Why are you interested in that stupid problem about the frisbee?" And Feynman says, "I don't know, but I am." And then he reflected on that and said, the really cool thing was, I was interested in it. I had no reason to be interested in it. It just was a really interesting problem. It's a math problem, if you want to look at it that way. And so he said, I got to figure that out. And so he did. And then you could say it's by chance, but it's not. You could say it's by chance, that's why he applied that solution to the hydrogen atom and the electrons, whatever he did, I don't know the details, but he ended up getting the Nobel Prize for it. And he's proud of that. That's why it happened.
Being able to follow your curiosity with just that purpose, which relates to the idea that you explained to me the other day about scientific, biological reductionism.
Right.
That's basically how it works, is that you open a box, and then when you open it, there's another one. And then when you open that one, there's another one.
Well, you got to figure out how to open each one. Each one is a Chinese box, okay? Think of it that way. You open the first, I spent a long time trying to figure out how to open it up. You open it up. Oh, no, there's another one inside. Now I got to spend another week figuring out how to take that one apart. So think of it as nested Chinese boxes. Each one is a challenge. Some people like working on puzzles, right? Sudoku, what's it called? I don't do it, but these word games, they just are fascinated by it. They're proud. They're good at it. That doesn't excite me. You would never catch me trying one of those puzzles because you can solve it, and that shows that you've got a good brain for doing that kind of thing, but it doesn't go anywhere. There's no second box inside. With reductionism, science is built on trying to understand how a neuron works, and then once you figured that out, then you say, well, all those neurons are connected to 10 to the 11th other neurons, and they all interact with each other, so what's that problem? How am I going to solve that one? And it's just a tediously slow process.
I don't know if you're aware, but there's actually a huge thing going on right now. There's a game called Wordle. Have you heard of it? Wordle? I think it's called.
I've heard of pickleball. Pickleball.
Yeah, but basically this game is like a word game. I don't really know how it works because I've never played it because it's the same thing. You solve it and okay, great. You solve it and there's nothing about it. But millions of people around the world are playing this game.
On the computer?
It's on the browser, the phone, anywhere. So it's basically about putting words together and like doing stuff like that. And actually, the New York Times just bought it for. They didn't say how much, but I think
What's it called again? Wordle? It's got word in there?
Wordle and then LE. I think that's what it's called.
I have.
Oh, you've heard of it?
Yeah, I saw it, but my eyes skipped over it and went to something else. But yeah, I remember now.
And even the New York Times just bought it for a couple $100 million or something like that. But it talks about the idea of like how people like solving these puzzles, but you solve it. That's it. I've never played it. I don't want to play it, but you sort of these things that you solve it and then.
So that doesn't motivate me even by the smallest amount. I'm completely uninterested in it. But there was another puzzle. It was a puzzle that I put it in my book, and I had a student, a young woman, and I showed her this puzzle, and she just went nuts trying to figure it out. And when she did figure it out, which she did, then wasn't interesting anymore, and she's gone. Okay, so the problem is it's a Chinese puzzle. You have stones, and you want to weigh things on a scale from 1, no pounds, they put no stones. 1 pound, you have a 1 pound stone. If you want to weigh 2 pounds, you have to have a 3 pound stone. You put a 3 pound stone on there, and you have 2 1 pound stones, and you take your 1 pound stone and you put it on there with the 2 pounds, and now you get a balance. So you didn't need another stone for 3. You got it? So 4, so now you got a 3 and a 1, so you can make a combination of that. So again, you didn't need another one. So how do you solve this problem? Well, you write down a matrix, and on over here you have these matrix, and you want to put plus, minus, and 0 in the rows, and you want the weights of the stones over here. So 1, 3, whatever they are. And then you multiply it out, and that has to come out to 1. And then you take the next row, and you multiply that out. They're called a dot product. So this is the stones. And you don't know what the stones are down there, but you're got to generate all the numbers from 1 to 40. So once you see that you can do this construction this way, it's a trivial problem. And it's fun because I enjoyed it, and I liked it because it was a math problem. And I had to formulate the math problem, say, this is like it's a matrix multiplication problem, and the elements in the matrix are either plus 1, minus 1, or 0. Can that work? And I'm going to figure out what the numbers are in this column, and I'm going to take these inner products, and am I able to I knew there was an answer because they said, find out what the minimum number of stones that you have. So I knew the answer had to be true, but how do you figure it out? When I saw this, doing these dot products, the elements are either minus 1, plus 1, or 0. So 0 means that stone doesn't get involved in that integer. And plus 1 means you got to have a stone that's 1 more. And minus 1 means you got to take one of your earlier stones and put it over there with the thing you're trying to weigh. And then you said, that's not too bad. And you only need, I don't remember, I think you only need 4 stones, 5 stones, something like that. It's a very small number. Of course, it's got to add up to 40. Anyway, it's a problem that I did like, but I've never looked at this wordy thing, but I doubt that I'm going to like it because it doesn't have a math solution. Right?
I don't know. Maybe. I don't
Word
know.
problems have huge numbers. The probability just goes off the charts because you take a 3-letter word and there's 26 letters for the first letter, 26 for the second, 26 for the third, so it's 26 cubed, but it's not because you have to do consonant, vowel. So it's much more complicated. And not all words are words. So it's a very much harder problem. And I don't know how to attack it. If I did, I'd probably be in a different business.
You've said many times that in your book you say that you've in your career as engineer, perhaps physicist and a little bit of mathematician, you said that you love making mistakes. What's been your favorite mistake?
Well, first, in the introduction of my book, I said I love making mistakes because I learn so much from them. Okay? I mean, if anybody tells you that they never make a mistake, they're lying to you. The way you learn is you make a mistake and then you figure out you did it wrong and then you learn. That's the process. So you've probably heard, don't be negative, always be positive. That's your philosophy, right? You have
Kind of.
openly stated that you're a person who... So there's a lot of ways of doing something wrong, but there's most of the time only one way to do it right. So if you can walk through life figuring out the right ways, every time you walk up to the door, you see two doors, and you open up the door, and there you walk into the hall, and there's two more doors. You open up the door, you walk in. Now, if you open the wrong door, there's a lion there that eats you. So if you could figure out by chance, you can't. I mean, if there's 10 doors, that's 1,000 possibilities. 2 to the 10th is 1024. So chances of you opening 10 doors in a row and getting every one of them right is 1 in 1,000. You're not going to do it. So that's life. You go and you try something and it didn't work. So you learned. You start learning the day you're born. And anybody who's not inquisitive won't learn and they'll be miserable. That's my interpretation of what'll happen. Everybody learns, or else they die.
I remember a quote I always think about is I think it goes, a fool never learns from his mistakes. A smart person learns from their mistakes. And a wise person learns from other people's mistakes.
That's good.
It's an interesting quote.
So you read books to learn about other people's mistakes, probably, right? That's a safe way to make mistakes.
What's been one book that you've gifted the most?
I can't answer that question because there isn't one book. I can't even... Brillouin's book on periodic structures. Okay, there's an answer. Brillouin is a famous physicist. He died probably in the 50s, and he's responsible for something called Brillouin zones. Léon Brillouin, I think that's how you pronounce his name. Léon Brillouin. It's French, but he was an American. I don't know if he was born in France, but anyway. And if you study quantum mechanics or semiconductor theory or whatever, you have crystals like silicon or germanium, whatever, and electrons go in there and they float around, and those are called semiconductors because sometimes the electrons freely move and sometimes they're blocked and they can't move. That's what that was the secret to understanding semiconductors, is understanding that. Now, whether an electron can move freely or it gets blocked, there's rules about that, and those rules are called Brillouin zones. They're named after Léon Brillouin. He figured it out and documented it and quantified it, and he wrote this book on periodic structures, waves. He's talking about electron waves in periodic structures. And that book is just simply amazing because it's got, but to answer the question again, when I was inducted into the professor army, I was made a professor, and the library said, we would like you to pick a book that is your favorite book. And then we'll buy a copy of it. And every professor has a book in the library that they picked.
Really?
Yeah. And I don't remember what book I picked. But it could have been Brillouin's book. But I don't think it was.
Can you go in and ask what's Dr. Allen's book? Or
Oh, yeah. They're in a special place in the library somewhere. There's probably a list. Some people picked some kind of silly books, like, Jane and Alice. I mean, I was kind of shocked by some of the books that people picked, something that was important to them in their childhood. It was important to them or they wouldn't have put it there, right?
Right.
I'm not criticizing them. I'm just surprised. The book that they picked was not intellectually challenging. Except when you're 3 years old, I guess. I don't know. I can't remember the details, probably on purpose, okay?
Okay, fair enough. I do want to ask you about, and know more about, your class, that the class you're teaching, Neuroscience for Engineers, which is, as you described it to me, talking about the science behind machine learning. So tell us more about how you find like the story of where you get that from, and also why the current machine learning class are probably not the best way to understand and make progress in this field of machine learning.
I have a feeling you're quoting me, and if I said that, I'm probably in trouble. But
My words.
yeah,
Okay?
no, but you got the sense of it that everybody's hot on machine learning, and I don't blame them. I mean, it's very successful. It's going a long way. It's doing good things. But what they teach you, my understanding of it is what they teach you in these classes is how to run the computer programs. And they have to train these computer programs to learn how to recognize things with, billions of examples. And they have a switching network. I call it a Boolean Hilbert space, which means that it's a high-dimensional space. Everything is a logical input and a logical output. It's these ones and zeros. You put in billions of ones and zeros and you get out. That is a picture of your grandmother. Show them a picture and they say, that's my grandmother when she was 12. You go, oh, how'd you figure that out? Well, because I saw a picture before. And so some people, smart people, who some of them were at Bell Labs, some of them whom I knew, still do. They figured out how to do this. And why were they inspired to do that? Because they learned about how the brain worked just enough. So there's a thing called the perceptron, which is a concept. McCulloch and Pitts came up with the idea, I think it's them, of the perceptron. The perceptron is a learning circuit, sort of. And it's based on neurons. The concept is based on neurons. You have a sum of millions of neurons all connected out there like this, fingers. They come in and they have synapses where they're joined together. And the synapses is like that problem I was telling you about the weights. You got to switch all of the weights just right. And if you get them right, bang, you can make a weight that's 17 pounds or 18 or 19 or 20 up to 40. And there's only one way to solve that problem. Well, how do you learn that automatically? Well, they figured out that this machine, there's a whole science behind it. There's books. And the book that so what happened? We got to cut this off because, it's getting late. But you can't be unaware. I hate double negatives. So I and everybody else was very aware of how much progress was being made in machine learning. But the problem from my point of view was there was all of these people just trying things randomly, which is the best way to do it when you don't know anything. But there was no science behind it. Yet I knew there was a science behind it because I had been working in the brain of the cat and I'd been working in the auditory system and I knew just enough to be dangerous. So I said, there's a science behind this and you guys aren't paying any attention to it. How are you going to figure this out if you don't have some science behind it? So I said, what we need is a course that teaches this. Now, I'm not going to have 200 students like the machine learning class, but if I have 10 or 20 students in the class and they really understand the principles, they're going to be the superstars in the future. And it's true. I put out a proposal to the curriculum committee, ECE. I said, I would like to teach this course. I said, what are your qualifications? I don't have any. Don't look at me. And here's the book I'd like to teach from. And they said, I got a lot of pushback on that. I said, that book was written 20 years ago. Why would you want to use that book? There's much more recent books. There's a lot of progress being made in this field. And you're not picking the book. You're picking some old book that's 20 years old. I said, well, are you telling the guy who's going to teach the course what book they should use? Well, they had to shrink back on that one. I said, well, the reason I'm picking that book is because it really covers the history. It explains that these people who proposed the idea that there's feedback in the brain, they all got rejected. They had terrible things happen to them. They were made fun of. But it turns out there's feedback in the brain. And Scott, in the book, he questions, why did this happen? He said, well, they didn't want to put feedback in the brain because it's too hard to solve. Well, that's not much of a reason, is it? So, did I say enough on that topic for now? Or do you have another question?
And what's the name of the book so people can know?
It's called Neuroscience, An Introduction to Neuroscience, a Mathematical Primer by Alwyn Scott. And you can get the PDF off my website, and it's readable by anybody. There's another book that's much more detailed. What's the guy's name? So anyway, I looked at the two books and I said, this book's too hard. We want something that's simple. It gives all the history behind it, talks about the basic papers, what's going on 100 years ago, what's going on 50 years ago, what's going on 20 years ago. That's good enough. This is the book I want. And I haven't looked back. I picked the right one.
The only time will tell when these people who are taking your class will be making the next discoveries.
No, I just gave the first exam, and on Monday and on Wednesday, we reviewed the exam, and much to my relief, everybody looked pretty happy, which I was glad. I didn't want them to fail. And there were some hard problems in there that they didn't get. But when they did, they were happy. Okay.
Yeah, I did look at the tests, and how I found it interesting is that you ask a lot of like conceptual questions about, tell me how this relates to this, or like tell me about who this was, or like that really like it blends a little bit of the history of how things came to be, but also a lot of practical questions. So you have some circuits, and you need to you ask people like write this equation this way and stuff like that, which I've so far taking a lot of math and engineering classes, never seen that thing. And I do have an intuition that perhaps learning a little bit of the history may give a deeper.
What you're talking about is Hodgkin and Huxley in the 1950s figured out how spikes propagate along nerve fibers. And they used a lot of electronics and a lot of stuff to do it. And they came up with a set of equations which don't make a particle of sense, but they do describe the phenomenon. And when I was teaching, this is the third time I taught it, when I first taught it, I said, that looks like an electrical circuit to me. And they knew it was an electrical circuit. They said there's potassium and sodium going across a barrier and all this stuff. And I said, I'm going to see if I can make a diode circuit. I mean, I thought I could do it with 2 diodes and 2 batteries, but it turned out I needed 3 diodes and 2 batteries. And it worked. And on Wednesday, that was yesterday, right? On Wednesday, I got up. I didn't get up, I was up. And I said, here's how this circuit works. And this was a question on the exam. So first you turn the pulse going in, and this diode turns on, and that diode turns off. And so it charges this capacitor, which is the myelin capacitor. And then the voltage goes off, and then that switch goes on, and this switch goes off. And so now it discharges through that capacitor through a different resistor. So you bought a bunch of switches, and they go on depending on how the voltage is that's coming in. And this very, very simple circuit explains Hodgkin and Huxley's model. They have these horrible equations, 3 diffusion equations that are nonlinear. They don't make any sense at all. There's no physics in them at all. And here is a circuit diagram. It's really simple. It's just a bunch of relays. A diode is a relay. And one guy said, I didn't understand it until now. Now I understand it. I said, the reason for that is that I didn't understand it either. I was forced into figuring it. I knew it worked because we had a working circuit, which was a slow process to get it to work. And at one time, I probably understood why this worked, but I didn't have it really down. And I have to teach this. It's on the exam. I really have to explain it. So I sat there and nailed it. And I got up, showed it, and the guy says, now I understand it. I said, good. So do I. Okay?
And then before I ask you the last couple of questions, was there any of other ideas that you wanted to talk about or bring up?
There's too many. I'll talk about one.
Perfect. Maybe the CO2 one, perhaps? Or
no, that's too complicated.
You choose.
There's something called Bernoulli Trials. That's a mathematical concept, but it's actually pretty simple. Although, the way people treat it. Okay, look, Bernoulli Trials. You have a coin, you flip it. It either comes up heads or tails. If you flip it 1,000 times, it's a fair coin. What's the average of the number of heads and the number of tails? They're equal, right? Yeah. So the odds ratio is how many heads do you get divided by how many tails? And that should be 1/2 for a fair coin. And that's, so you're flipping the coins and you say, how many times do I have to flip it to know that it's a fair coin? Well, there isn't any answer to that question because it depends how close. If you flip it 10 times, there's a very high probability you'll get 10 heads in a row. And you'll think it's an unfair coin, but you're completely wrong. You have to flip it 1,000 times and then you'll know that it's a fair coin. So there's a very, very important question. Goes back to Daniel Bernoulli. How many times do you have to flip it so that you can estimate the odds ratio, which is the probability of heads to tails, the number of heads, the number of tails? Well, if I told you one time, you'd tell me I was crazy. But I'm going to tell you a problem where one time is the answer. Let's say you want to know if you have COVID. You go get tested. So no, 0. Get tested again, 0. Get tested again, 0. Get tested again, 0. You get 100 tests and you're 0. One day you go in there and you get tested and you're positive. Are you positive or not? You are positive. And it depends on the false positive rate. Now you got tested 100 times and it never came up positive one time. 100 times in a row, it's negative. And then one day you get a positive. You know you're positive. And all you have to do is get tested again 2 times in a row, and you are positive. Now, if you told somebody that with Bernoulli trials, you only need to get one head to know that it's not a fair coin, or, there's a question you have to ask carefully. So nobody would say one time, except somebody who really understands the problem, and you ask them that question and they say one time. But the number of people that'll say that are rare. So this is a nice little story. I'm going to stop on this one, okay? There's a guy by the name of Laplace, famous mathematician. And somebody asked him, what's the probability that tomorrow the sun won't rise? And he came up with the right answer. He said, let's assume that the sun has risen 5,000 times. So the probability that it won't rise tomorrow is 1 over 5,001. This is the same problem as the COVID test, right?
Exactly.
If you've had a lot of observations and every single time it happened, the best answer is that it won't happen is you add 1, you divide the number of times you've seen it plus 1. That is the odds. And that's the best you can do. Now, he doesn't know about nuclear fission, that the sun is made of hydrogen and the hydrogen is burning up and E equals mc squared. He doesn't know any of that. But he's a good mathematician, so he gives you the right answer. And the mistake people make when they think about Bernoulli trials is they think this coin has a bias and I want to find it. Well, that's the wrong question. It's not a stationary coin. It was a one-headed coin until one day it became a one-tailed coin. So it's a non-homogeneous process. That's the real problem. And as far as I know, that's not the problem they talk about. They talk about, if you flip the coin, how many times does it take? What's the probability? What are the odds? Bernoulli polynomials, all sorts of gobbledygook. It's very interesting. Mathematics, but completely irrelevant. So it's a fun problem. It's extremely important.
And yeah, I'm currently taking a statistics and probability class. And if if it wasn't because of you, I probably would have never heard of the Bernoulli trials and also the Laplace sunrise problem. I believe it's called
Sunrise hypothesis.
sunrise hypothesis. There you go.
So is your class talked about Bernoulli yet?
I don't think so. I mean, they don't necessarily say like Bernoulli per se, but they mostly talked about some of the theorems that he sort of developed.
N choose K.
But they never mentioned who Bernoulli was or how he did it.
Well, there's a lot of math associated with it, but none of the math talks about non-homogeneous processes. It just assumes that the odd ratio is a fixed number and you're going to compute everything, give you a lot of homework problems on it, and you end up scratching your head. You have, well, what is the point of all of this? Well, the point is one trial and you're positive.
Why should one learn statistics or probability?
Hmm?
Like why should one learn statistics or probability?
Oh, I think it's extremely important. But the way it's taught is so obscure that I remember, I want to stop this conversation, but it's not happening. I was taking a course in random processes at the University of Pennsylvania, and the teacher was very, very good. And one day I went to class, and I wasn't following very well what was going on. And then he said, right out of his mouth, he says, since 1 + 1 is equal to 1. And I said, oh my God, I'm in big trouble. It's basically, if you have two truths, then it's true. You have true plus false. You don't know. If it's two false, then the output is false. So he was just talking logic, how, Boolean logic. And he did it on purpose. And I got it. Then I knew I was in deep, deep trouble. Because we were halfway through the course. Anyway, let's end on that.
Last question. From everything you've learned in your 78 years of life, what advice would you give a driven and ambitious college student as they take on their life?
Okay. Number one, try to figure out what you like and don't ignore it. But if you find something out that you like more than that, go for it. Don't get stuck in a hole because when you were 6-year-old, you liked something. So I knew I was good at a certain kind of thing. And it was so easy for me that I said, I don't want to do that because it's too easy. So I didn't. I avoided it. And then I failed a whole bunch. And then one day I said, what I am good at is actually quite useful. So just get off your horse and start working on the things you're good at. When I made that decision, I'm losing my voice. When I made that decision, it was like a 90-degree turn and 180 degrees. And I started going the other direction, and I started becoming successful. Because I identified something that I was good at. And I was good at it.
And you're talking about circuits.
Well, I don't want to try to define too carefully what it was I was good at.
Okay.
Because I'm not sure I can even remember. But I knew there were certain things that I could do very easily. They probably did not include language because I couldn't spell. I think Einstein was dyslexic, right?
Something like that.
Yeah. So I think I don't want to get into this. I think I could explain what's going on in the brain at this point. I've read enough neuroscience, and you have visual memory, right? You have auditory memory, which is bigger. Well, there's 1 million nerves in each eye, and there's 50,000 or 30,000 in each ear. So there's a lot more neurons coming out of the eyes than there are coming out of the ears. A lot of the process is happening right there in the eye. That's why Jerry Lettvin got in trouble and he lost his funding, because he said the processing is going on in the retina. They said, you are no longer going to be funded. That's the craziest thing we've ever heard. Of course, he was right. Okay, no more questions.
Perfect. All right. Thank you very much, Dr. Allen. I think talking to you has really inspired me to seek out and really find the things I like and really learn what it's like to open a box and open the other one. And open a box and open the other one.
I'm not in the slightest bit worried about you. You're highly motivated. You're trying to figure things out. And you are going to figure them out.
At least I'll try.
Maybe I can accelerate the process a little bit by showing you how to do it. But you read that paper that I gave you about Hamming. That's a pretty amazing document.
Almost done.
He's so critical of everybody, but there's a message in every criticism. He went so far as to say somebody was stupid, which is not a very nice thing to say. It probably wasn't true. It just wasn't. Okay, stop.
All right. Thank you very much.